Hi, I'm Paul Peterson.
Hi, I'm Leslie Finger. In this section of the Methods lecture, we are discussing the meaning of a standard deviation. Paul, let's start at the beginning. What is a variable?
Well, it's not a small animal that lives in the Arctic, which is sort of what I thought when I first heard the word, but it is anything that varies, as I learned in the first textbook I ever read on this topic. So, for example, people vary in height. Therefore, height is a variable. People vary in weight. Weight is a variable. So if all people were the same height, then height would not be a variable. It would be a constant because it doesn't vary. So it's pretty simple. Variables vary.
Okay, so what is a standard deviation?
Well, that's a little bit more complicated. It is essentially the amount of variation in the variable. It's how much dispersion there is around the average value within a population. Standard deviations are useful because you can compare different variables with one another even though they are ordinarily measured in different units. So let's go back to height and weight. In this case, we measure height in feet and inches, and we measure weight in pounds and ounces. So it's hard to say, is this person tall for their weight, or is this person heavy for their height? But when you measure height and weight in standard deviations, you can figure this kind of thing out. So in education, we use standard deviations all the time because we want to compare student performance on many different tests. And by converting all of the information to standard deviations, we're able to compare performance on one test with performance on another test. We can also do this for groups of students.
When people talk about standard deviations, they often display a diagram that is called a bell curve. What is that?
The bell curve. You can see it right here, and it has this nice shape to it where it shows that most of the people are in the middle of the distribution, and only a few people are out on the edges of the distribution, what we call the tails of the distribution. And it's a surprising fact that many variables actually have the distribution of a bell curve. That's why it's popular with statisticians.
Can you give us an example of a variable that has a bell curve distribution?
Well, let's go back to height. In the case of height, men tend to be on average 5 feet 10 inches, and they tend to vary, most of them, within one standard deviation of 3 inches. So 2/3 of the population will fall within that, and that's exactly what this bell curve tends to show. We do the same thing with tests. We find out whether or not the distribution of one group as compared to another varies in such a way that one group, on the whole distribution, is more on the positive side, that is a higher performance, than on the downside.
But why are test scores on standardized tests almost always normally distributed within a large population?
Yeah, now that's a good question because it's the fact that the people who construct these tests like bell curves and they write the questions in such a way as to get a normal distribution. But it's also because people's performance on tests tend to have a normal distribution, just as we get it with height. We tend to get it with test score performance. So the two things blend together, and we tend to get, in most cases, tests that have that very valuable property that psychometricians love to see.
But why do those who design tests want a normal distribution?
Well, in that way you can easily compare one test to another. So we want to say sometimes we want to compare the test performance on the NAEP with the test performance on the PISA. And if we convert both tests to a bell curve distribution and calculate the standard deviation, well, then you are in good shape. You can say that the two tests are giving you much the same information or not giving you that information if indeed they show up with different results.
Why can't we just compare the simple test results? Scores were higher in reading than in math, say.
Well, that's a good question too, because a lot of people would prefer that. Oh, how many did you get right on your reading test? Well, what if the reading test is a hard test? And what if the math test is an easy test? If we do it that way, then it would look as if a student is really good in math and not very good in reading, when exactly the opposite is the case. But by converting everything to a standard deviation, we can compare the performance of a student or a group of students on the reading test with their performance on the math test.
I get it. Standard deviations put everything into comparative framework. One is always looking at how well an individual or group is doing compared to others. Still, it's odd to be told that one group is doing one standard deviation better than another. How can we translate this back into something that ordinary people could actually understand?
Well, I personally think that the best way to do this when one is talking about standard tests is to use some examples of how test performance has emerged in different countries. So let's take the 2012 PISA test, for example. The average student in all industrialized nations scored 494 points in 2012. The average student in the United States scored 481 points on this graph. Now that's 13 points lower than the average for all the countries in the industrialized world. And we also can see that Japan scored 536 points, which is 42 points higher than the average OECD country. So simple calculation tells us that Japan scored 55 points better. They answered 55 questions more accurately as compared to the United States, or some equivalent to that.
But what does that 55 points really tell us? Is this where we can use standard deviations to help us?
Yes, indeed. That's a very good way to put it. So the standard deviation makes meaning out of that number 55. Once you know that the standard deviation for the PISA in 2012 was 92 points, then you can convert that 55 points and that 13 points for the United States into standard deviations, so that it becomes 14% of a standard deviation, or 0.14, you can say it either way, below the average, and you can say that Japan's performance was about 0.46 above the average, or 46% of a standard deviation, and from that you can say, okay, the Japanese scored about 60% of a standard deviation better than the average student in the United States. And that tells us that a student who scored among the top third of students in the United States would be only average in Japan. Now that tells us something that we can't get just by looking at that number 55.
Can you give me another education example?
Well, if 8th graders take the 4th grade test, they will do about 1 standard deviation better than the 4th graders on that test. So that tells us that students learn about 25% of a standard deviation a year between 4th grade and 8th grade.
That seems really important to know. How can we apply this?
Well, we often want to know whether or not a program or a policy, say it's class size reduction, or say it's a new merit pay program for teachers, whether it really has an effect on student performance and whether that's a big effect or not. So let's say we find out that it affects a student performance. Let's say class size reduction actually increases student performance by 12% of a standard deviation. Well, that's about a half year's worth of learning. So by converting all these numbers into standard deviations, and then standard deviations to something meaningful, we're able to think about whether or not the interventions that are recommended as ways of improving education are actually working. This is a tough topic, standard deviations, but I think we can get our hands around it if we have another chat, again with Josh Goodman, economics professor at the Kennedy School, who's familiar with these materials. A standard deviation is a very complicated concept if you're not a statistician.
Right.
So how do you explain what a standard deviation is? You know, in education research, scholars talk about it all the time. So how do you explain this to an ordinary person?
So I think you start by saying that different tests are scored in different ways. And so when you, as a researcher, want to compare how kids are doing on different tests, you need some way of making these tests look similar. And so we take the test scores if it's 0 to 100 or the SATs that go up to 1600, and we scale them in such a way that we can compare the tests to each other. And we do this by expressing kids' scores not in terms of points, but in terms of standard deviations, which tell us how far along the kid is compared to his peers. I think one way to think of it is when economists talk about a standard deviation, the difference between a kid who's right in the middle and a kid who is one standard deviation farther along on a given test is that the kid in the middle is at the 50th percentile of the distribution, and the kid who's one standard deviation along is at about the 83rd percentile. So that's a pretty big difference. And I think one way to think of it as an education researcher is when we worry a lot about achievement gaps in the United States. And so if you think about the gap between low-income children and high-income children in most settings in the United States, that gap is about one standard deviation on most test scores. It's similar for the black-white achievement gap. And so when we think about educational interventions that have certain effects, we can benchmark it by thinking that a one standard deviation gap is sort of roughly the size of the difference between low and high.
So if we are going to get racial equality on achievement tests, we got to move the test scores up one standard deviation for disadvantaged African American children.
That's right. And so very often education researchers will evaluate policies and may come to a conclusion that a given policy moves test scores by 1/10 of a standard deviation, for example. And that sounds like a small number, but what you're really saying is that that kind of intervention might have the capability of closing 1/10 of that achievement gap between poor and non-poor kids, black and white kids.
Not enough, but better than nothing.
Exactly.